Assalamualaikum and hi, my name is Modern Algebra and my matrix number is S74234. So in this video, our group are going to explore one of the most important results in group theory, which is a Lagrange theorem. I will start first with some introduction of the Lagrange theorem. So, group theory is a branch of mathematics that deals with algebraic structure called groups. It helps us understand symmetry, structure, and operations, not just math, but in real-world application like cryptography, coding theory, and even puzzles like the Rubik's Cube. So, Lagrange theorems shows a special relationship between a group and its subgroups. It tells us how their sizes or orders are connected. So in this video, we will look at the statement of the theorem, a simple proof, some examples, and also a few cool applications.
Statement of Lagrange theorems: if G is a finite group and H is a subgroup of G, then the order of H divides the order of G. Mathematically, this means that the order of H divides the order of G, or the order of G is equals to the index of H in G times the order of H.
Let's now take a look at how Lagrange theorem works without getting too technical. Suppose we have a finite group G and a subgroup H. We can divide the elements of G into a separate blocks called cassettes of H. So each cassette has the same number of elements as the subgroup H, and none of them overlap. This means the whole group G is made up of these equally sized cassettes. So the total number of elements in G, which is written as you can see on the slide, is just a number of cassettes times the number of elements in each cassette, which is the size of H. Mathematically, this is written as you can see on the slide. I already show how to write where G and H is the number of cassettes of H in G. These equations show us that the size of H divide the size of G exactly, and that's how what Lagrange theorem says.
To fully understand about Lagrange theorems, we need to be familiar with several fundamental ideas from group theory. Here are some key terms with simple explanations and examples. The first one is group. A group is a set G together with a binary operation that satisfies these four properties, which is closure, associativity, identity element, and inverse element. The second one is subgroup. A group of H of a group G is a subset of G that is itself a group under the same operation. That means H is a subset of G. The operation from G works within H. H contains the identity of G, and H is closed under the operation and taking inverse. The third one is order. The order of a group G is the number of elements in the group. The order of a subgroup H is the number of elements in H. Let me give an example using the group Z seeds, which is the integers modulo seeds under additions. The order of Z seeds is 6 since it has 6 elements, which is 0, 1, 2, 3, 4, and 5. Now, consider the subset 0 and 3. This is a subgroup of Z seeds generated by 3. It has 2 elements, so its order is 2. The fourth one is cossets. Given a subgroup H of a group G and an element G is in capital G, a left cosset is the set as you can see in the slide. Each cosset is a shifted version of the subgroup. All cossets of H in G have the same number of elements as H and they do not overlap. The group is divided or partitioned into these cossets. The last one is the index of a subgroup. The index of H in G is the number of distinct whether left or right cossets of H in G. So, the index of H in G is equal to the order of the group G divided by the order of the group H. This is why the order of group G is equal to the index of H in G multiplied with the order of group H, which is the core idea behind Lagrange theorem.
Let's go through a simple example using the group of 6, which is just a numbers 0 to 5 with addition modulo 6. When we pick a subgroup 0 and 3, this means we only looking at 0 and 3 from the groups. Now we make cosets by adding each number in Z6 to the subgroups. 0 plus 03 will be 03, 1 plus 03 will be 14, 2 plus 03 will be 25. So we get 3 cosets. That shows the subgroup has 2 elements, the full group has 6 elements, and 2 divide 6 which match Lagrange theorems. You could also use other example like permutation groups or cyclic groups.
So moving on to the application and importance of Lagrange theorems. First one is it helps in proving other theorems. Cauchy theorems stated that if a prime P divides the order of a finite group G, then G has an element of order P. Lagrange theorems helps justify why only certain elements orders are possible. The second one is Lagrange theorems helps constrain possible subgroup orders. The theorems tell us that the order of any subgroup must divide the order of the group. This gives us an easy way to rule out certain subgroup sizes. The third one, it helps in group classification. Lagrange theorems exist in classifying finite groups. By knowing the size of the group and possible subgroup sizes, mathematicians can narrow down the structure and properties of unknown groups. Last one, Lagrange theorems can be applied in physics and chemistry. For example, in symmetry analysis, especially in physics and chemistry, groups describe rotations, reflection, and other transformations. Lagrange theorems supports the understanding of which symmetry subgroups are possible for molecules, crystal, or quantum systems.
So for the conclusion, restate the theorem in simple terms, emphasize its usefulness and foundational role in group theory, mention how it connects to real-world application or higher level math.